just a decade or so before, in 1950, Alan Turing wrote the paper that formulated the Turing test. And he opened that paper with the question, can machines think? So let me ask you this question. Can machines think? Can your ice cube tray one day think?
Um, Certainly machines can think, because I believe you're a machine and I'm a machine, and I believe we both think. I think
Speak for yourself.
I think any other philosophical position is sort of a little ludicrous. What does think mean if it's not something that we do? And we are machines. So yes, machines can, but do we have a clue how to build such machines? That's a very different question. Are we capable of building such machines? Are we smart enough? We think we're smart enough to do anything, but maybe we're not. Maybe we're just not smart enough to build stuff like us.
The kind of computer that Alan Turing was thinking about, do you think there is something fundamentally or significantly different between between our ears, the biological computer that humans use, and the computer that he was thinking about from a sort of high level philosophical?
Yeah, I believe that it's very wrong. In fact, I'm halfway through I think it'll be about a 480-page book. The working title is Not Even Wrong. And if I may, I'll tell you a bit about
Yes,
that book.
please.
So there's three thrusts to it. One is the history of computation, what we call computation.
Mm-hmm.
It goes all the way back to some manuscripts in Latin from 1614 and 1620 by Napier and Kepler, through Babbage and Lovelace. And then Turing's 1936 paper is what we think of as the invention of modern computation. And that paper, by the way, did not set out to, invent computation. It set out to negatively answer one of Hilbert's three later set of problems. He called it as an effective way of getting answers. And Hilbert really worked with rewriting rules, as did Church, who also, at the same time, a month earlier than Turing, disproved Hilbert's one of these three hypotheses. The other two had already been disproved by Gödel. So Turing set out to disprove it, because it's always easier to disprove these things than to prove that there is an answer. And so he needed, and it really came from his professor while he was an undergrad at Cambridge, who turned it into, is there a mechanical process? So he wanted to show a mechanical process that could calculate numbers, because that was a mechanical process that people used to generate tables. They were called computers, the people at the time. Mm-hmm. And they followed a set of rules where they had paper and they would write numbers down, and based on the numbers, they would keep writing other numbers. And they would produce numbers for these tables, engineering tables, that the more iterations they did, the more significant digits came out. And so Turing, in that paper, set out to define what sort of machine could do that, mechanical machine, where it could produce an arbitrary number of digits in the same way a human computer did. And he came up with a very simple set of constraints where there was an infinite supply of paper, the tape of the Turing machine, and each Turing machine had came with a set of instructions that, as a person could do with pencil and paper, write down things on the tape and erase them and put new things there. And he was able to show that that system was not able to do something that Hilbert had hypothesized. So he disproved it. But he had to show that this system was good enough to do whatever could be done, but couldn't do this other thing.
Yeah.
And there he said, and he says in the paper, I don't have any real arguments for this, but based on intuition. So that's how he defined computation. And then if you look over the next, from 1936 up until really around 1975, you see people struggling with, is this really what computation is? Mm-hmm. And so Marvin Minsky, very well known in AI, but also a fantastic mathematician, in his book Finite and Infinite Machines from the mid-'60s, which is a beautiful, beautiful mathematical book. Says at the start of the book, well, what is computation? Turing says it's this, and yeah, I sort of think it's that. It doesn't really matter whether the stuff's made of wood or plastic. It's just, that relatively cheap stuff can do this stuff. And so, yeah, it seems like computation. And Donald Knuth, in his first volume of his, Art of Computer Programming in around 1968, says, well, what's computation? It's this stuff, like Turing says, that a person could do each step without too much trouble. And so one of his examples of what would be too much trouble was a step which required knowing whether Fermat's last theorem was true or not, because it was not known at the time. And that's too much trouble for a person to do as a step. And Hopcroft and Ullman sort of said a similar thing later that year. And by 1975, in the Aho Hopcroft and Ullman book, they're saying, well, we don't really know what computation is, but intuition says this is sort of about right, and this is what it is. That's computation. It's a sort of agreed upon thing which happens to be really easy to implement in silicon. And then we had Moore's law, which took off, and it's been an incredibly powerful tool. I certainly wouldn't argue with that. The version we have of computation, incredibly powerful.
Can we just take a pause? So what we're talking about is there's an infinite tape with some simple rules of how to write and on that tape, and that's what we're kind of thinking about. This is computation.
Yeah, and it's modeled after humans, how humans do stuff. And I think Turing says in the 36 paper, one of the critical facts here is that a human has a limited amount of memory. So that's what we're going to put onto our mechanical computers. So, unlike mass or charge or it's not given by the universe. This is what we're going to call computation.
Yeah,
and then it has this really, it had this really good implementation, which has completely changed our technological world. That's computation. Second part of the book, or argument in the book, I have this 2x2 matrix with science in the top row, engineering in the bottom row. Left column is intelligence, right column is life. So in the bottom row, the engineering, there's artificial intelligence and there's artificial life. In the top row, there's neuroscience and abiogenesis. How does living matter how does non-living matter become living matter?
Yes.
4 disciplines. These 4 disciplines all came into the current form in the period 1945 to 1965.
That's interesting.
There was neuroscience before, but it wasn't effective neuroscience. It was, there were these ganglia and there's electrical charges, but no one knows what to do with it. And furthermore, there were a lot of players who are common across them. I've identified common players except for artificial intelligence and abiogenesis. I don't have, but for any other pair, I can point to people who worked in them. And a whole bunch of them, by the way, were at the Research Lab for Electronics at MIT, where Warren McCulloch held forth. And in fact, McCulloch, Pitts, Lettvin, and Maturana wrote the first paper on functional neuroscience called What the Frog's Eye Tells the Frog's Brain, where instead of it just being this bunch of nerves, they sort of showed what different anatomical components were doing and telling other anatomical components and, generating behavior in the frog.
Would you put them as basically the fathers or one of the early pioneers of what are now called artificial neural networks?
Yeah, I mean, McCulloch and Pitts. Pitts was much younger than him. In 1943, had written a paper inspired by Bertrand Russell on a calculus for the ideas immanent in neural systems, where they had tried to, without any real proof, they had tried to give a formalism for neurons, basically in terms of logic, and gates, or gates, and not gates, with no real evidence that was what was going on, but they talked about it, and that was picked up by Minsky for his 1953 dissertation on which was a neural network, we would call it today. It was picked up by John von Neumann when he was designing the EDVAC computer in 1945. He talked about its components being neurons, based on, and in references. He's only got 3 references, and one of them is the McCulloch-Pitts paper. So all these people, and then the AI people and the artificial life people, which was John von Neumann originally.
There's like overlap between all of them.
They're all going around at the same time. And 3 of these 4 disciplines turned to computation as their primary metaphor. So I've got a couple of chapters in the book. One is titled, Wait, Computers Are People? Because that's where our computers came from.
Yeah.
From people who were computing stuff. And then I've got another chapter, Wait, People Are Computers? Which is about computational neuroscience.
Yes.
So there's this whole circle here. And that computation is it. And I have talked to people about, well, maybe it's not computation that goes on in the head. Of course it is.
Yeah.
Okay, well, when Elon Musk's rocket goes up, is it computing? Is that how it gets into orbit? By computing? But we've got this idea, if you want to build an AI system, you write a computer program.
Yeah, in the sense, so the word computation very quickly starts doing a lot of work that it was not initially intended to do. It's like in the same, if you talk about the universe as essentially performing a computation.
Yeah, right. Wolfram does this. He turns it into computation. You don't turn rockets into computation.
Yeah. By the way, when you say computation in our conversation, do you tend to think of computation narrowly in the way Turing thought of computation?
It's gotten very, squishy.
Yeah.
Squishy.
Okay.
Over time. But computation in the way Turing thinks about it and the way most people think about it actually fits very well with thinking like a hunter-gatherer. There are places, and there can be stuff in places, and the stuff in places can change, and it stays there until someone changes it. And it's this metaphor of place and container, which, is a combination of our place cells in our hippocampus and our cortex. But this is how we use metaphors for mostly to think about. And when we get outside of our metaphor range, we have to invent tools which we can sort of switch on to use. So calculus is an example of a tool. It can do stuff that our raw reasoning can't do, and we've got conventions of when you can use it or not. But sometimes, people try to, all the time, we always try to get physical metaphors for things, which is why quantum mechanics has been such a problem for 100 years, because it's a particle. No, it's a wave. It's got to be something we understand. And I say, no, it's some weird mathematical object that's different from those, but we want that metaphor. Well, I suspect that 100 years or 200 years from now, neither quantum mechanics nor dark matter will be talked about in the same terms. In the same way that Phlogiston's theory eventually went away because it just wasn't an adequate explanatory metaphor. That metaphor was the stuff. There is stuff in the burning. The burning is in the matter. Whereas it turns out the burning was outside the matter. It was the oxygen.
So our desire for metaphor and combined with our limited cognitive capabilities gets us into trouble.
That's my argument in this book. Now, and people say, well, what is it then? And I say, well, I wish I knew that. I'd write a book about that. But I give some ideas. But so there's the 3 things. Computation is sort of a particular thing we use. Can I tell you one beautiful thing?
Yes,
thing I found.
please.
So, I used an example of a thing that's different from computation. You hit a drum and it vibrates, and there are some stationary points on the drum surface. Because the waves are going up and down, the stationary points. Now, you could compute them to arbitrary precision, but the drum just knows them. The drum doesn't have to compute. What was the very first computer program ever written by Ada Lovelace? To compute Bernoulli numbers. And Bernoulli numbers are exactly what you need to find those stable points in the drum surface.
Wow.
Anyway, and there was a bug in her program. The arguments to divide were reversed in one place.
And it still worked.
Well, no, she never got to run it. They never
Oh,
built the
obviously.
analytical engine. She wrote the
Yeah.
program without a,
So computation.
Computation is sort of, a thing that's become dominant as a metaphor, but
Yeah.
is it the right metaphor? All three of these four fields adopted computation, and a lot of it swirls around Warren McCulloch and all his students, and he funded a lot of people, um, and our human metaphors, our limitations to human thinking, all
Yes.
play into this.